Hi, everyone. Our discussion of quantum mechanics is focused recently on particles bound by different types of potentials. We've discussed the infinite well potential, a finite well potential, and today we're going to introduce another one called the quantum harmonic oscillator, where the particle is bound in the potential like a mass on a spring. There's a spring-like force that's pulling it back towards the origin. Okay? The result of this problem turns out to be rather important because it seems there are many, many physical systems that are approximated rather well by the quantum harmonic oscillator. And these range from things which are obviously connected, like the vibrational modes of molecules, to things which don't seem to be related at all, like the quantization of the electromagnetic field into photons, and yet do turn out to be described by the same mathematics. Okay, well, it's such an important problem, actually one of the most important that we're going to talk about, that we may as well go ahead and get started. Here, let me turn to the notebook and show you an outline. All right, well, here's our outline for today. We've recently talked about free particles and bound particles, and I'll spend a moment today reviewing our results for the infinite well and the finite well very quickly. But then we're going to go on and talk about the quantum harmonic oscillator. And here we'll introduce the potential, for the harmonic oscillator, and then calculate the energy states. For this system. Then we'll have a look at the wave functions for the particle bound in this potential. And finally, we'll look at some examples. Okay? All right. Well, here, let me first quickly review what we found out for the infinite well and the finite well, just to warm us up. Oh, excuse me. Okay. All right. The first problem we looked at was the infinite well. And we found that for a particle trapped in an well with infinite walls that has width L, that the energy states of the system could be found pretty easily. And we found a series of states, n equals 1, n equals 2, 3, 4, and so on. And we found these obeyed a simple equation. The energy of the nth state was given by h squared over 8m L squared times n squared, where n is a quantum number that can take on values 1, 2, 3, 4, and so on, non-zero positive integer values. Okay? We also looked at the finite well, which is sort of a cousin of the infinite well, the much more practical cousin, right? Because there are no systems that are actually exactly like an infinite well, but there are many that approximate it, and most of them are better approximated by a finite well. In the finite well, the barriers have a finite height, U0. And we found that in this system also, we could find energy states. Now there's only a finite number of energy states. let's say 3, but it could be as small a number as 1 or as large a number as, well, any number, depending on the system that we're looking at. Okay? In this case, the energy states were determined by an equation, but it's not a simple equation. Instead, we found an equation for the energy, an implicit equation that looks like this. For even states, we found that KL over 2 had to be equal to alpha over K, where alpha and K are terms that depend only on the energy, so that this is an implicit formula for the energy. And for odd states, we found a slightly different formula. Okay, there we go. Now, for both of these systems, we found the wave functions for the states. For the infinite well, the wave functions look like the wave functions that might describe standing waves on a string. Okay? So they have nodes at either end of the box. Excuse me, let me try that one again. And then in between the nodes, there are sinusoidal functions. All right? Okay. For the finite well, we got something that was qualitatively similar, but with an important distinction. Now the wave function does not go to 0 at the boundaries of the box. Instead, it leaks out into the barrier. Okay? So that the wave function is sinusoidal or oscillatory inside the well and is a decaying exponential outside of the well. They're rather more complicated, but that's what we found. Okay? All right. Well, the next thing we're going to do is to talk about the harmonic oscillator. In the harmonic oscillator, the potential looks like a parabola. Here, let me show you. So the potential looks something like this. It's shaped like a parabola. Okay? One similarity to the infinite well is that in our simple model, the potential continues to increase like a parabola without limit as we move away from x equals 0. Okay? That's the quantum harmonic oscillator. All right, and we're going to turn and consider this in more detail in the next video.